In this video, we're going over the review sheet for circles quiz number 2. So since this line segment over here is tangent to the circle at this point, the point where a tangent to a circle meets a radius is where a right angle is formed. Remember, a tangent to a circle and a radius of the circle are perpendicular, form right angles where they intersect. So I know that here I have a right triangle. I also know that this whole distance from here to here is 4 plus r, because remember, to get a whole, if you have two parts, you can combine them together with addition. And this side of the triangle is r. So using the Pythagorean theorem, since I do have a right triangle, I can set up an equation. One of the legs squared, so that's a squared, I just used the 12 side, plus b squared, I'm writing b, but I want to write r, because r is the other leg of this right triangle, is equal to the hypotenuse squared. And the hypotenuse is 4 plus r squared. Now, since I have 4 plus r squared, I'm going to have to use FOIL. So let me write it out over here. 4 plus r times 4 plus r. That is 16 plus 4r plus 4r plus r squared, which is 16 plus 8r plus r squared. Let me write that down over here. And that's equal to 12 squared plus r squared. From here, I'm going to solve the equation using inverse operations. So I'm going to just subtract r squared from both sides. And here I have 12 squared, which is 144. I can just rewrite that as 144. Is equal to 16 plus 8r. I'm going to subtract 16 from both sides. And 144 minus 16 is 128. And then divide both sides by 8. We get r is equal to 16. And that's answer choice number 1. For question number 2, we are told that lines AE and BD are tangent to the two circles in the picture. We know the ratio from AC to CE is 5 to 3. So I can represent AC as 5x. That doesn't look like a 5. Let me redo that. And I can represent CE as 3x. I know the whole length of BD is 56. And what we need to do is find the length of CD, of this part over here, from C to D. Well, since we know that two tangents that come out of the same external point, two tangents drawn to a circle from the same external point, are congruent to each other, we know that AC and BC are congruent to each other. And I also know that CD and CE are congruent to each other because, once again, they're two tangents to circle P coming out of the same external point C. So I can also represent BC the same way as AC with a 5x. And I can represent CD the same way as CE with a 3x. Since I know that the whole segment BD is 56, I can make an equation that says the two parts of BD, 5x and 3x, combined together, that's addition, will give us 56. From here, I can combine like terms. I have 8x is equal to 56. And we can finish up solving the equation by dividing both sides by 8. And that gives us x is equal to 7. We're not done because the question isn't asking for x, it's asking for the length of CD. So we do have to plug back in. CD is represented as 3x. So 3 times 7 equals to 21. And we found that the length of CD is 21. 3 is very similar to 2. Once again, we have tangents to the two circles here that are drawn. And we know the ratio from TA to AC is 1 to 3. So I can represent TA as 1x, or just x for short. And I can represent AC, as 3x, because that's the 3 parts of the ratio. We are told that the whole line segment TS is 24. And we need to find the length of SE. So we need to find the length of the purple part. Just like in the previous example, when we have two tangents drawn to a circle from the same external point, they are congruent. So notice how tangents TA and TE, they're both drawn from the same external point T, and they're both tangent to circle Y. So they are congruent to each other. So if this is X as well. Notice how TC, this whole line segment over here, is tangent to circle X at point C. And notice how TS is also tangent to circle X at point S. Since TC and TS are both tangent to circle X and are drawn from the same external point T, that means they are congruent to each other. So the whole line segment TC, the whole tangent, I should say, and the whole tangent TS are congruent to each other. So we can make an equation that says if we take the two parts of this tangent and add it together, since we know one part's x and one part's 3x, if we combine the two parts, it should be equal to 24. Because since the two tangents TC and TS are congruent, if TS is 24, TC should also be 24. So I'm going to make that equation over here. 3x plus x is equal to 24. So we have 4x is 24. Dividing both sides by 4, we have x is equal to 6. Now the question was asking for the length of SE. So in order to figure that out, I know x is 6. So that's TE over here, that's 6. So I'm going to do 24, the total, minus 6. And that gives me 18. There we go. In the next question, we are looking for the length of BD in miles. Let me take a look at the question and mark the diagram real quick. So it tells us that the road between cabins G and L is 8 miles long. So 8 miles long and is tangent to the lake. And it also says that the path between cabin L and dock D, so here from L to D, is 4 miles long. And we're looking for the length of BD. So I'll label that with a question mark over here. Or I can just label it with an X. That's probably easier instead of a question mark. So remember, whenever we have segments of a circle that we want to find the length of, and the segments are partially located outside of the circle, as we have here, we have a tangent that's outside the circle, and we have a secant here that's partially outside the circle. We use this formula, whole times outside equals whole times outside. So I'm going to write that here, whole times outside equals to whole times outside. So I'll start with the tangent. The whole tangent is 8 times the outside part of the tangent, while the whole tangent is located entirely outside of the circle. So the outside part is the same thing as the whole, since it's entirely located outside of the circle. So that would be 8 again. So whole was 8, outside part was also 8. That's equal to the whole secant. The whole secant would be the x part and the 4 part together. That's 4 plus x. Remember, if we have two parts, we put them together with addition. So 4 plus x times the outside part of the secant, which would be 4. I'm going to start off by distributing the 4 inside the parentheses. And 8 times 8, that is 64. We have 16 plus 4x. From here, we can just solve the equation. We can subtract 16 from both sides. So we have 48 is equal to 4x, and then dividing both sides by 4, I have x is equal to 12. And X does represent BD. So we have 12 is the length of BD. And that's answer choice number 2. Okay, moving down. Here we are told that AE is X, EB is X plus 1, CE is X minus 1, and ED is 2X. And we are looking for AE. So we are looking for the segment represented as X. Since we're finding segment lengths and the segments are located inside the circle, we don't have any outside parts of the circle, we can't use whole times outside equals whole times outside like we did in the last example. The reason for that is that none of the segments here have any parts outside of the circle, so we wouldn't have anything to use for any of the whole or outside parts. So instead, what we're going to do here is we're going to use our rule for intersecting chords, finding the measurements of the segments. And that is part of one chord times the other part is equal to part of one chord times the other part. So the product of the parts of the chords should be equal to each other. Let's set up the equation. So on this chord, on chord DC, we have one part here and the second part here. The first part is 2x. Second part is x minus 1. So that product should be equal to the two parts of the other chord AB. So that's x plus 1 and x. So let's solve our equation. Let me get a little bit more space here. Distributing inside the parentheses, I have 2x squared minus 2x is equal to, let me also distribute the x squared plus x. Okay, now I'm going to subtract x squared from both sides, and I have x squared minus 2x is equal to x. Then, so I can get all the x terms in one spot, I'm going to subtract x from both sides. I have x squared minus 3x is equal to 0. I can factor by pulling out the x, and that leaves me over with x minus 3. So we have two solutions here. We have x equals 0 and x equals 3. It doesn't make sense for x to be 0 because if AE had a length of 0, we wouldn't be able to see it. There would be no segment there if it has no length. So we're going to reject the 0 just like we often reject the negatives in geometry because we're talking about like shapes and segments and objects. And if those were negative, you wouldn't be able to see them either. They wouldn't, be able to be drawn. So we have our solution here, x equals 3. And that is the length of AE that we are looking for. Okay, if anyone needs the work, you could pause right now. Okay. In the diagram below, quadrilateral ABCD is inscribed in circle P. We need to find the measurement of ADC. So keep in mind, whenever we have a quadrilateral inscribed in a circle, we call that a cyclic quadrilateral. And one property of cyclic quadrilaterals is that the opposite angles are supplementary. That means they add to 180. So if this angle here is 110, the angle across from it should be 70 degrees. That makes 180. If this angle is 72, the angle across from it, which is the angle that we're looking for, should be 180 minus 72. And that gives us 108. You could also use properties of inscribed angles, since we do have a bunch of inscribed angles here, to help figure that out. But I think it's just easiest in this situation to use the property of cyclic quadrilaterals, that opposite angles are supplementary. And then we answered the question in 2 seconds. For number 7, we have a sprinkler here, and the sprinkler is rotating according to this diagram, the shaded part of the diagram. And it's asking us to find the area of the lawn. So basically, we're finding the area of the sector here. Remember, a sector is just a section of a circle. So we're finding the area of the shaded sector. So we're told that the angle is 300 degrees, and we do need to know what the central angle is. So I'm going to write that down. Remember, to find sector area, we have a proportion very similar to the arc length proportion. Sector area over whole area, so I mean area of the whole circle, is equal to central angle over 360 degrees. I'm going to use the 360 and not 2 pi because my angle is given to me in degrees. If it was given to us in radians, we would use 2 pi instead in the proportion. So let's just plug in. We're finding the sector area. If the radius is 15, then 15 times 15 squared is 225. So 225 pi would be the area of the whole circle. And that's equal to central angle over 360. It does say to the nearest square foot. So we are going to be rounding. Our answer is not going to be in terms of pi. So we can cross multiply. I have 360x is equal to, let me multiply 225 by 300, is equal to 67500 pi. And then from here, I'm just going to divide both sides by 360. You can type the pi into your calculator because you are being asked to round. Pi should not be in your answer. You should get a rounded decimal answer, but you are rounding to the nearest foot, the nearest square foot. So you're rounding to the nearest whole number. Putting it into my calculator now, getting my fraction button. I have 67500 times pi, and I'm dividing that by 360. So I got approximately 589 square feet. Okay, in number 8, they actually tell us what the area of the sector is. They tell us it's 2 pi centimeters squared. So that's the area of the shaded sector in the diagram. They are telling us that the length of NL is 6, and they want us to find the measurement of angle N. So if the diameter LN is 6, that means the radius of the circle is 3. So since they give us the sector area and they give us the radius, we need to find the central angle that made the area of the sector. Once we find that central angle, then we can use it to help us find the angle that we are looking for. So I'm going to set up a proportion like we did before with sector area because we are given the area of a sector. So sector area over whole area is equal to central angle over 360. Once again, I'm going to use 360 degrees. You can use 2 pi if you want your angle to end up being in radians, since we are solving for an angle. But just taking a look at the answer choices, since this is a multiple choice question, all of the answer choices are in degrees. So that kind of tells me that I want to use 360 so that my answer will end up being in degrees and not radians, and I won't have to do a conversion after, because that's annoying if we could just end up with our angle in the units that we need it in according to the answer choices. So the sector area that we're given is 2 pi centimeters squared. The whole area of the circle is pi r squared, so that's 9 pi. And that's equal to the central angle, which we're solving for, over 360. So I'm going to cross multiply and solve for the central angle. So that's 720 pi is equal to 9 pi times theta. Dividing both sides by 9 pi, we have 720 pi over 9 pi. there's a pi in the numerator and the denominator, so the pi's cancel out. And 720 divided by 9 is 80. So we just found that the central angle is 80, but be careful. That's an answer choice, but that's not what we were looking for. We weren't looking for the central angle of the shaded sector. We were looking for angle N over here. So I do know that central angles are congruent to the measure of their intercepted arcs. And I do know that angle N is an inscribed angle. It's got its vertex on the circle. And inscribed angles are half the measure of their intercepted arcs. Angle N does intercept arc ML. Notice how it's opening up to it. Both of its rays are opening up to arc ML, so it does intercept arc ML. So angle N is half of its arc, which would make it 40 degrees. So the answer choice here is 3. That is correct. Okay, for number 9, let's take a look over here. We got a lot of stuff going on in this picture. We're told that angle P is 40 degrees, and we're told the measurement of arc, the ratio of the measurement of arc CD to arc DA is 1 to 8. So I'll represent this as 1x or just x, because CD is the one part of the ratio. And I'll represent DA as 8x. The first thing that we are looking for is the measurement of arc AD. So I see that, oops, let me highlight that a bit better because my highlighting's messy. I see that arc AD is almost half of the circle, but I see that the full arc ADC over here does make half of a circle. So since I know that arc ADC entirely should make 180 degrees, and I know that AD is 8x and DC is x, I can make an equation that says x plus the 8x part of the arc should give us a semicircle, should give us 180 degrees. So here I have 9x is equal to 180. So dividing 180 by 9, I have x is equal to 20. So that tells me arc CD is 20. And that tells me arc DA or arc AD, if I substitute in, that's 20 times 8. And that's 160 degrees. So we just answered the first part of the question. The measurement of arc AD is 160 degrees. Next, the question is asking for the measurement of arc AB. So taking a look at arc AB, and let me just erase my yellow from before so it doesn't get in the way of the new stuff that we're doing now. So I see that arc AB, let me outline it right over here, is one of the two arcs intercepted by the secants to the circle. So notice how if I highlight both of the secants, I guess this is not the secant, this one's a tangent. We have a secant and a tangent. Sorry about that. Secant intersects the circle in 2 spots. Tangent only intersects at 1 spot. I was thinking it was long, so I was thinking it hit the circle in 2 spots, and it only hit 1. Doesn't matter for our purposes right now. Same thing regardless, but just to get that vocabulary right. So we have our tangent and our secant opening up to arc AB. It's intercepting arc AB, and it's also intercepting arc AD. So remember, the outside angle, anytime you have an outside angle, whether it's formed by a tangent and a secant, 2 tangents, or 2 secants, an outside angle is equal to half the difference of the intercepted arcs. So I know that the 40-degree angle, and I'll just do the work over here, the 40-degree angle is equal to half the difference of big arc minus small arc. So big arc we found before was 160. That was what we found in part 1. That was arc AD. Minus small arc which is AB, that's what we're looking for, I'm going to represent that as x. So I'm going to start off by multiplying both sides by 2 so we can get rid of that 1/2. Then I'm just going to subtract 160, so I have 80 minus 160. That is negative 80. And then we can finish up by dividing both sides by negative 1. And we have that x is equal to 80. So we just figured out that arc AB, and I'll just erase the x here so we can replace it, is 80 degrees. I'll write it here also. That really doesn't look good over there. I'll try to change that to being 80 degrees. Okay. Next up is the measurement of angle BEA. So in order to figure out the measurement of angle BEA, I'm just going to erase all my highlighting from before because once again, I don't want it to get confusing with the new thing that we're solving for now. There we go. Perfect. All the colors are gone. So angle BEA is right over here, and it's one of the two vertical angles that we see right over here. Those are both congruent. So if we find the measurement of one, we find the measurement of the other. And this vertical angle here, BEA, opens up or intercepts arc AB that we just found the measurement of. And this vertical angle over here opens up to or intercepts arc CD, which we already found was 20. So remember, the vertical angles, whenever we have intersecting chords, or you can also think of it as anytime we have angles inside the circle that we're solving for, are equal to half the sum of their intercepted arcs. So if I call this x, the angle that we're solving for, I know that the angle that we're solving for is equal to half the sum that's plus of the intercepted arc. So that would be 80 and 20. Now remember, the theorem I'm using again is for when you're solving for an angle that's inside the circle or when you're given an angle inside the circle. You can also think of it as an angle formed by intersecting chords. And the angle inside the circle is half the sum of the intercepted arcs. So let me distribute the 1/2 here. So I have x is equal to 40 plus 10. So I have x is equal to 50. So angle BEA is 50 degrees. Let me put that here. Next, we're being asked to find angle BAC. So angle BAC, once again, I'm going to just get rid of the yellow markings so that it doesn't interfere with what we're talking about now, all the markings, so it's not distracting. Okay, so angle BAC is an inscribed angle. Notice how its vertex is on the circle. So I do know that it's half the measure of its intercepted arc. So if we can find what its intercepted arc is, then we can take half of that and we'll have the angle. Luckily, we know what the other arcs of the circle are. This is the only one that's missing. And all the arcs of a circle altogether should add up to 360. So I'm going to do 80 plus 160 plus 20. Those are the other arcs that we found so far. And I'm going to do 360 minus that sum. So minus 260, that's what I got as the sum. And I got 100 degrees for arc BC. So that makes the inscribed angle that intercepts that arc 50 degrees because half of 100 is 50. Okay. The last thing this question is asking us to look for is angle PBA. So angle PBA is this angle right over here. Oops, things are popping up here. And once again, just so that we're not distracted by all the other markings, I'm just going to take a second and erase. Okay, and the angle that we're finding is angle PBA. BA. So angle PBA is an angle that's on the circle. And remember that anytime you have an angle that's on the circle, it's equal to half of its intercepted arc. So since its intercepted arc, BA, is 80 degrees, that angle should be 40 degrees because once again, it's on the circle and angles on the circle are half of their intercepted arc. We also, in order to find that, we also could have used the fact that there's a triangle BAE, and now we know two angles of the triangle. We know 50 and 50, so we could use that to help us figure that out as well. But I think the easiest way is just to say that this is an angle on the circle, so it's half the of its intercepted arc. Oops, keep clicking the wrong thing there. So I have some of the questions for the first proof covered because I don't want to display the written proof until after we discuss it together. So the first thing I'm going to take a look at is my proof statement, and I see that I'm proving a proportion. And before we prove a proportion, we do first need to prove that two triangles are similar to each other. So I have BC, AB, CA, and EC. So let me start by determining what triangles I'm proving similar to each other. So BC is from this triangle, and it looks like AB is connected to that, so I'm going to put them in the same color, and that's one triangle. So that leads me to believe that the other two sides are from the other triangle, so that's CA. I do see that, and EC. So that tells me the second triangle I'm proving similar. So at first, before even marking your diagram, you might notice that they do share a side AC, but I want you to keep in mind that if you're proving triangles similar, congruent sides don't help you because that doesn't show that they're proportional. And for SAS or SSS for similarity, you would have to show proportional. You'd have to have numbers or some reason to believe that they were proportional to each other. Congruent sides are not going to help you. So we're looking for AA. That's usually how we prove two triangles similar in two-column proofs without numbers. So that's what we're going to be looking for. We do know that we have a tangent to the circle. Let me move a little bit so we can kind of see the question. So we know that tangent EC is drawn to diameter AC. So here's tangent EC. It's drawn to diameter AC. Remember that when a tangent and a radius or a diameter meet at the point of tangency, they are perpendicular to each other. And perpendicular lines form right angles. We're also told from our givens that chord BC is parallel to secant ADE. Now that's important because we do know that when we have parallel chords in a circle, they intercept congruent arcs. The arcs in between these chords, these parallel chords, are congruent. And the arcs connecting these parallel chords would be these two. So I do know that arc AB and arc DC are congruent to each other. I have the right angle in the purple triangle, so I want to try to find a right angle in the green triangle. So if you weren't able to find it, it is angle B. And the reason that angle B is a right angle is because an angle inscribed in a semicircle is a right angle. Notice how angle B is an inscribed angle. Its vertex is on the circumference of the circle. And notice how the intercepted arc of this angle is AC, which is half a circle. It's a semicircle, which is 180. So that makes angle B have to be 90, half of its intercepted arc. So simply we can put that as an angle inscribed in a semicircle is a right angle. And already we have one pair of congruent angles because all right angles are congruent to each other. From there, I'm going to look for another pair of congruent angles. So I see that this angle over here, angle BCA, intercepts arc BA, and I see over here that angle CAD intercepts arc CD. And we already showed that AB and CD, those two arcs are congruent to each other. So if we have inscribed angles that intercept the same arc or congruent arcs, then those inscribed angles are congruent. The reason for that is if we have two inscribed angles, the measure of inscribed angles are half their intercepted arc. So let's say that this arc was 80, this one would also be 80. Both of the inscribed angles would be 40. They would be the same because they intercept congruent arcs. Now we have AA showing that the triangles are similar. From there, we can prove the proportion. It's the same reason every time. Corresponding parts of similar triangles are proportional. Specifically, corresponding sides of similar triangles are proportional. I'm going to remove this so you can take a look. Notice how all of the steps that we just mentioned in the diagram are listed in the proof. I mentioned that angle C is a right angle, and how we knew that. A tangent and a diameter are perpendicular to each other at the point of tangency, and perpendicular lines form right angles. I combined that into one step because I didn't want to put in one step that AC and CE were perpendicular, and then in a second step that this was a right angle. So I just put it all into one step. Then I mentioned how I knew that angle B is a right angle. An angle inscribed in a semicircle is a right angle. I mentioned that angle C and angle B are congruent to each other. That's because all right angles are congruent. We also need to make sure that we mention that arc AB and arc CD are congruent. If it's in your diagram, it should be in your proof because parallel chords intercept congruent arcs. So then we can conclude that angle BCA and angle CAD are congruent to each other because inscribed angles that intercept congruent arcs are congruent. Notice how I also mentioned that BCA and CAD were inscribed angles before I said they were congruent to each other. From there, we have the two triangles are similar by AA. And then finally, the proportion. Corresponding sides of similar triangles are in proportion. In the next proof, we are told that DB is tangent to the circle at point B. We're told that we have chords in the circle, and we're told that C is the midpoint of arc AB. So we know if C is the midpoint of arc AB, then it's splitting arc AB into two congruent smaller arcs. So that tells us that arc AC and arc CB are congruent to each other. Notice how angle CBD is on the circle. It's formed by a tangent and a chord. We spoke about in class how when we have an angle on the circle, it is half the measure of its intercepted arc. We also know that angle ABC is an inscribed angle because its vertex is on the circle. And we know that inscribed angles are half the measure of their intercepted arcs. So since both of these angles are half of their arcs and their arcs are the same, then they should be the same as each other as well. Let me show you that written up in a proof. So notice that all the steps on my proof are exactly the steps that we just marked in the diagram. I started off by mentioning that AC and BC or CB were congruent to each other because we knew that C is a midpoint and a midpoint splits an arc into two congruent parts. Then I wrote that angle CBD, this angle here, is half of its intercepted arc. And the reason for that is an angle formed by a tangent and a chord. You can also say an angle on the circle is half of its intercepted arc. Then I mentioned that angle ABC is an inscribed angle because its vertex is on the circle. And we know that angle ABC is half of its intercepted arc because inscribed angles are half the measure of their intercepted arcs. Finally, we can say that CBD and ABC, the two angles, are congruent to each other due to substitution. The reason that I didn't say transitive property is because transitive property is when two things are congruent to the same third thing. So as you can see from steps 3 and 5, CBD and ABC, one of them is half of CB ABC is half of AC. Now, I know that CB and AC are the same as each other. We mentioned that in our proof. We see that from the midpoint. So it might look like transitive property, but technically, to use transitive property, there should only be 3 names of things involved. And here we have 4 things involved, even though these two are the same. So that's why I use substitution. Substitution is a more general version of the transitive property. The transitive property is a specific case of substitution for when you have 2 things congruent to the same third thing. So when only 3 things are involved. If 4 things are involved, like here, substitution would be the way to go. When in doubt, I would say to use substitution since it is the more general case of the transitive property. For the last proof, we are proving the theorem that if a secant and a tangent are drawn to a circle from an external point, the product of the lengths of the secant segment and external segment equals the length of the tangent segment squared. So basically, we're proving whole times outside equals whole times outside. That's just the long way of writing that theorem, but it's whole times outside equals whole times outside what we're proving. And they gave us the product that we're proving over here at the bottom, AC times AD equals AB squared. I'm just going to write that out. So instead of writing AB squared, I'm going to write AB times AB. So it looks a little bit more like the products we're used to proving because AB squared is AB times AB. So I see that we're proving a product. So I know before I can prove a product, I need to prove a proportion. And before I can prove a proportion, I need to prove 2 triangles similar to each other. So I need to figure out which 2 triangles I need to prove similar to each other. Because now that I drew in segments BC and BD, like the hint told us to in the question, we need to figure out the 2 triangles that we're actually going to be proving similar. So I'm going to just outline the parts of the product here so we can see which triangles we are proving similar. So AC, that is right over here. And next we have AD. So AD is actually this whole line segment. So that's coming from the big triangle. As you can see here, if I outline AD, that's coming from the big triangle. And then we have AB. So AB shows us that we're focusing on the small triangle in green times AB, while AB is also another side of the big triangle. So we can see here that the 2 triangles that we are focusing on are the small one in green and the large red triangle. So be careful. If you're trying to prove the 2 smaller triangles are similar to each other, that's not going to help you accomplish your goal. We're proving that the big triangle and the small one outlined in green are similar to each other. And once again, that's coming from the segments mentioned in the product. So use the product, or if it's a proportion, use the proportion to help you figure out which 2 triangles you are focusing on. If you're focusing on the wrong triangles, you are never going to reach the end of your proof. Okay, so I already see that the red and green triangles share angle A. So that's congruent to itself by the reflexive property. I see that angle BDC over here is an inscribed angle. Its vertex is on the circle. So I know that it's half the measure of its intercepted arc, which is BC. I also know that angle ABC right over here is an angle on the circle. It's formed by a tangent and a chord. It's on the circle. So it's equal to half of its intercepted arc. And its intercepted arc is also BC. So I see here that angle BDC and angle ABC are congruent to each other because they are both half of their intercepted arcs, and their intercepted arcs are both BC. It's both the same thing as each other. So now we have that the triangles are similar to each other by AA. We have the shared angle between both the triangles. That's one pair in each. That's one pair. Then we have this angle in the small green one, congruent to this angle in the large red one. So that's our second pair of congruent angles for AA. Once we prove the triangle similar by AA, we can prove a proportion involving the corresponding sides. Let's talk about that after we see the beginning of the proof. So I'm going to display my proof up until proving the triangle similar, and then we'll talk about the rest of it. So notice up until this point in my proof, I mentioned everything that we mentioned out loud. So we always start off with our givens. And then the hint said to draw in segments BC and BD to make triangles. Those are called auxiliary lines, which means extra lines that you add into a diagram in order to make things like easier to see and easier to work with. Here, the purpose of adding them in was to make triangles, because if we didn't have triangles, then I don't know how we would prove this product, because we need to first prove triangles similar in order to prove the product. So I'm going to write down that word over here, auxiliary lines. So in my proof, I actually had to mention that we drew in those auxiliary lines because that wasn't given to us in the question. So I wrote chords BC and BD were drawn. You can write auxiliary lines. BC and BD are drawn into the diagram. And the reason that justifies it is simply that 2 points determine a line. We had point B and C, so I can draw a line through them. We had points B and D, I can draw a line through them. So simply any 2 points determine a line justifies these extra lines, these auxiliary lines we're adding in. Then I mentioned the shared angle, angle A, between the big and the small triangle. It's congruent to itself by the reflexive property. I mentioned that this angle BDC is an inscribed angle because its vertex is on the circle. And then, since it's an inscribed angle, we do know that it's half the measure of BC, its intercepted arc, because inscribed angles are half the measure of their intercepted arcs. Then we can mention angle ABC, which is also half the measure of its intercepted arc. Once again, that's because an angle formed by a tangent and a chord, you can also just call it an angle on the circle, is half its intercepted arc. Since angle BDC and angle ABC, those two angles in our diagram, are both equal to half of the same arc, they're both equal to half of arc BC, we can say that they're congruent to each other. And that's by the transitive property, because there are three things involved. There's the two angles, and they're equal to the same third thing. So that means they're equal to each other. So that's transitive property. Now we have our two pairs of congruent angles for AA, proving that the triangles are similar. From there, we just need to prove a proportion and then prove the product that we're proving. So in order to figure out the proportion, you can test out the segments from the product in a proportion and just make sure that they cross multiply to give you the product that you need. Otherwise, you can take the means and divide them, take the extremes and divide them. So I can divide the means, which I have in purple, that's AC over AB, equals 2. Let me divide the extremes. I have them underlined in red, AB over AD. And that should always cross multiply to give you the product that you need. AC times AD, that is what we need. AB times AB, that is what we need. That's AB squared. So over here, I have the proportion. And the reason is corresponding sides of similar triangles are in proportion. Remember, when you're proving a proportion, the same reason can be used every time to justify it. And finally, right after that, we are proving the product. And for proving the product, it's the same reason every time as well. In a proportion, the product of the means is equal to the product of the extremes. And we are done. Make sure to also review your constructions. Constructing a circle center, constructing a hexagon and equilateral triangle inscribed in the circle, constructing a square inscribed in the circle, and this got messed up over here, but it says circumscribing a triangle. That means drawing a circle around it by first locating the circumcenter. And inscribing a triangle, that means drawing a circle inside of a triangle by first locating the incenter and constructing a tangent to a circle. Remember that all of the steps for these constructions can be found on Google Classroom under Unit 5 classwork. It is posted as a material.